Hello everyone, welcome back. Today we're going to continue with the question paper, grade 12 of mathematics paper 2. We are going to have a look at question 9, which focuses on cycle geometry. Um, so straight up, we see there's a diagram, and in that diagram we are given a center O, and we are being told that the points S, T, and R on the side, the circle here, and then there is a chord ST, TR, and then SR, as they are drawn here, and then there's a tangent QS. So the question is asking us to prove that the angle QST is equal to the angle R. When I say it again, QST. Please have a look at the previous video. I'm going to attach the link which explains the terminology or the way of naming angles. So when we say QST, we are focusing on the angle in between. So QST refers to this angle here. And then they are saying prove that it is equal to R, which is that angle in there. So what is this about? As you might remember or recall, when we have a tangent and we have a chord, then they're asking us that, or they're telling us this angle is equal to that one. We usually refer to that as the tan-chord theorem. So that's normally what we apply in circle geometry, but then today they're asking us to prove how did they get to that. And when you prove these theorems, do know that you are allowed to use other theorems to prove a certain theorem. It's not that you need to define or try to go from first principles which have no link to any other theorems. So we're going to prove the tan-chord theorem using the existing theorems. So yes, we're trying to prove that this guy is equal to this one. The first thing we must note is that it's better for us to add. So when you prove, do draw on the sketch that you're given. When you're drawing in there, you're creating your own diagrams that will help aid to solving the question. So the first one we're going to do is that, if you notice, so if we're to draw a line from the center to exactly that point on the circle, that line, we call it a radius. It's a radius because from the center to the circumference. And what this line does is that it intersects with the tangent at this point S. And if you might recall, there is a theorem that says that a line from the center, so a radius intersecting a tangent forms or intersects the tangent at 90 degrees or perpendicular. So we know that OS is perpendicular to QS. Why? Line is a line perpendicular to radius. That is the theorem. So if this is perpendicular, it means that we have a 90 degrees in here. We have a 90 degrees. I'm going to add or give you a trick in that even though we are already given these angles, you are allowed to say from in terms of making sure that you can prove the angles or making things easy for you, you can just name this angle here 1 and this one 2. So we have S1 and S2. We're supposed to prove that S2 is equal to R. So from here we can already have an equation that says that S1 plus S2 is equal to 90 degrees. This is just using the statement before. So when we add S1 and S2, they should give us 90 degrees. Alright, so we already know that. Then we can write S2 has that S2, so therefore S2 is equal to 90 degrees minus S1. So that's our first equation that has S2, which is the angle of interest. Then we ask ourselves, how can we link this angle to S1? That's the second step. So you'll notice that, like I said, draw on the diagram. So if you had to draw a line from here to here that touches the circumference, that line is also a radius. And you should see that. So if this is a radius and a radius, then of course they are equal, and we're forming a triangle in here that has this shape where one or two of the sides are equal and the other one not equal to the others. So this triangle is called an isosceles triangle because there's two sides that are equal. And the other characteristic of this triangle, so this triangle is like this: O, T, and S. So in this triangle, this angle is equal to this angle. So we can call that angle, so we divide it into T1 and T2. We also divide this into O1 and O2. O2 is on this side. O1 plus O2 should give us 360. So that's a revolution. And then T1 and T2 at this point, we don't have a specific angle because T1 is not a tangent, or no, so ST is not a tangent and RT is also not a tangent. So we don't have any characteristics in here. But what is of interest here is that if these are equal, it means that S1 is equal to T1. So we have S1 equals to T1 because isosceles triangle. Because also in here it's isosceles because OT is equal to OS, and you must make sure that you draw these so that the person who marks you can see your drawings. It's very important to show your line of thought. So S1 is equal to T1, which means we can write T1 as S1. So we can literally say S1 here is also, there's also S1 in here because T1 is equal to S1. But also what we know is that if this is O1, a summation of these angles in here must give us 180. So O1 plus S1, which is here, plus T1, but then we know T1 is the same as S1, so plus S1. This should give us 180. So that is the sum of angles in a triangle is equal to 180. So sum of angles in a triangle is equal to 180. So we can already see that S1 plus S1 is going to be 2S1. So we have that O1 is then equal to 180 minus, so we take the summation of this and send it to that side. We have O1 equals to 2S1. Do you see that? And then from here, we already know that S1 can be represented into S2. And we do that by saying S2 is equal to 90 minus S1, or we take S2 to this side and we substitute by whatever the value of S1 will be in this equation 1. But before that, let me tell you where we're going with this thing. Now that we've found this angle, we know that this angle is twice this angle. Why? So angles, so angles subtended by the same chord, and then there's an angle at the center, then the other one is at the circumference. The one in the circumference is equal to half of the one at the center, and that's the theorem that says angle at the center is twice the angle at the circumference. So we also know that O1 is equal to 2 times R. And this is angle at center is twice angle at circumference. Please finish that. So what is how do we link up all of this? So if O1 is equal to this, so this is equation 2, and then this one is equation 3. So O1 is equal to this, and then O1 is also equal to this. It means we can equate these two. We can equate these two, and because of space, I'm going to just go back to the previous instances of this video to check what was written in here. I'm going to erase this guy. So we have that now 2R is equal to 180 minus 2S1. But also we know that S1 can be rewritten in here. When you rewrite S1, you have that S1 is equal to 90 minus S2. How do you do that? We take S1 to the left, so the sign changes to positive, and take S2 to the right and the sign changes to the negative. So we then come and substitute this guy here. So we have 180 minus 2 times this 90 minus S1. There, the S2, there it is. So if you multiply 90 by 2, so negative 2 by 90 is going to be 180 minus 180, then minus, so this one and this one by this one. Negative times negative is going to be positive. Then we have 2S2. So we can already see that 180 minus 180 is 0. So we have that 2R is equal to 2S2. And dividing by 2 here, we have that angle R is equal to S2. But then, so S2 is literally the angle that they wanted us to prove with. So QST. And the reason here is tan chord theorem. That's it. It's very easy to prove this theorem. That's if you understand the basics or all other theorems, and that you make it easy for the person who marks you to see how are you drawing all of, so the lines that you are telling us about OT, and OS, they were not there in the first diagram, so you need to properly draw that, and you must draw it on the same diagram they have given you. So that's it for proving the tan chord theorem. Thank you.